Hello friends, and welcome to Webronaq. Here is a question worth pausing on. Take any polynomial, something like x squared minus 2x minus 3, and try to find a hole in it. A gap, a jump, a place where the function just breaks down. You will not find one. Polynomials are perfectly continuous everywhere, and that is not an accident. It follows directly from the rules of limits. But to really understand why, we need to be precise about what continuous actually means, because the intuition of no gaps is a great start, but it is not a proof. So let us build this up from the ground floor, starting with the formal definition of continuity at a point. Alright, so what does continuity at a point actually mean? Mathematicians nail it down with three conditions. First, f of a must be defined. The function has to produce a real output at the point you care about. Second, the limit of f of x as x approaches a must exist. This means the function settles toward a single value as you close in from both sides. Third, and this is the key condition, that limit must equal f of a. The value the function approaches must match the value it actually takes. All three conditions together. If even one fails, you have a discontinuity. This three-part test is the standard, and it is exactly what we will now verify for polynomials. Next, let us look at the limit laws that make that verification almost automatic. Here is the interesting part. We do not have to evaluate polynomial limits by some exotic technique. We have three limit laws that do the heavy lifting. The sum law says the limit of a sum equals the sum of the limits, provided each limit exists on its own. The product law says the limit of a product equals the product of the limits, same condition. And the constant multiple law says you can pull a constant factor right out in front of the limit sign. Together, these three laws mean you can disassemble any polynomial into its individual terms and factors, evaluate each piece separately, then reassemble the result. The only ingredient you still need is one foundational fact about what the limit of x itself equals. That is exactly where we go next. Now let us put it all together. The one foundational fact we need is that the limit of x as x approaches a equals a. That is essentially the definition of how limits work for the identity function. From there, apply the product law once, and you get the limit of x squared equals a times a, which equals a squared. Apply it again for x cubed, and so on for any power. Then apply the constant multiple law to each term, pulling coefficients out front. Finally, apply the sum law across all the terms. The result is that for any polynomial p, the limit of p of x as x approaches a equals p of a. The function is defined at a, the limit exists, and the limit equals the function value. All three continuity conditions are satisfied, everywhere, for every polynomial. So here is the through line. It all starts from one simple fact. The limit of x as x approaches a is just a. From there, the product law, the sum law, and the constant multiple law let you disassemble any polynomial, evaluate every piece, and reassemble the answer. The result is that the limit of any polynomial p of x, as x approaches a, always equals p of a. That means direct substitution is not a shortcut. It is mathematically guaranteed, and this matters beyond polynomials too. Rational functions are continuous wherever their denominator is not zero, and many composite functions inherit continuity from their polynomial components. The groundwork you just saw is the engine behind all of it. Thanks for watching, and we will see you in the next one.